Welcome, everyone. I'm going to be presenting a talk entitled An Empirical Approach to Cognitive Science. During the talk, I'm going to talk about cognitive science and how to study the mind. I'm going to cover a range of topics, including the state of cognitive science as a field, whether the human mind is a computer, what happens if you feed the mind its own Gödel sentence, what it means to feed the mind its own Gödel sentence, and why introspection is a great way forward for understanding human cognition. The point of this talk is to set the stage for a discussion of introspection. It's not very much about introspection itself, which may seem strange until one realizes exactly how much stage setting is needed if people are going to start thinking about alternative approaches to studying the mind and taking those seriously. I will say a few things about introspection specifically at the end, but most of the talk is going to be about cognitive science and what it means to approach it empirically. The elephant in the room for introspection, so to speak, is the computer. Psychology seems incredibly out of date. My impression, at least, is that at some point people gave up on psychology and moved on to neuroscience. And at some point, maybe gave up on neuroscience and moved on to AI. When you think about where people actually expect breakthroughs to come from, it's not psychology, and it's definitely not introspection. With neuroscience, you may expect people to say, well, we figured out that the X region of the brain has been linked to speech or something like that, but that's about it. The fact that people's focus has moved on from psychology is hidden to a degree by the existence of the modern field of statistical experimental psychology. This field at least has the form of a science, as numbers and technical papers exploring hypotheses. You get the occasional Nobel Prize in economics. These things are happening, but there are clues that people's actual focus is no longer on that as a way of understanding the mind. One of the clues is that the field of experimental psychology has been in an announced state of crisis for more than a decade, and simplifying a little bit, no one seems to care. Another is that literally no one is expecting a major breakthrough, for instance, on the level we're seeing in AI, to come from the field of experimental psychology. At this point, you get studies, sometimes they provide cool insights, they provide ideas, but you don't really know if the stuff is true. People aren't really expecting anything more. So did people stop caring about the mind? I think the answer is no. Rather than giving up entirely, the energy was transferred, sublimated, if you will, into a nearby field that, as it turns out, neither I nor any of my teammates at Leverage had studied closely, and that's the field of cognitive science. Leverage had looked at the history of psychology before. I personally studied the prehistory, which includes philosophers like Plato and Kant, Hume, etc., as well as manuals for how to direct the mind with the goal of discovery by people like Descartes and Spinoza. Some of our researchers looked at the time after the field really got going, looking at Fechner with psychophysics, Wundt Titchener with structuralism, Freud with psychoanalysis, and then behaviorism. I'd looked into the current field of statistical experimental psychology, but as far as I know, none of us had ever really closely studied cognitive science. I wasn't planning on studying cognitive science in the near term either, but I was recently following a trail as a result of studying quantum biology. I was learning about quantum biology. This led me to Roger Penrose, and that to Gödel's incompleteness theorems. And by the time I was reading Gödel, Escher, Bach by Douglas Hofstadter, I realized, okay, what I'm doing right now is studying cognitive science. This was an opportunity to plug a gap in my and Leverage's understanding. So once I realized that that's what I was doing, I began to look into it more deliberately. One of my first steps was to check the Wikipedia entry on cognitive science, with the basic question being, what is cognitive science? Is it a science? If it's a science, what are its foundational discoveries? I was soon surprised, and you can do this right now. If you look at the Wikipedia article on cognitive science, you can scroll down and see there's a heading key findings. And you'll see that there aren't any real discoveries actually listed there. It could be that that's just a bad part of maybe this is a dark part of Wikipedia that hasn't been fixed up. They also have a list of notable researchers, but mostly they're listed for developing hypotheses or philosophical arguments or helping to get the field going. The fact that there weren't, here are the foundational discoveries led me to continue to ask the question of whether cognitive science was actually a science. Now, to be clear, it's okay for fields to not yet be real sciences. Many of the social sciences are not real sciences, at least not yet. When things get named, they are frequently named aspirationally. So when you name a thing a science, you're doing so not because you necessarily have established a science, but because you're doing it in anticipation of a science coming into existence. I think naming things aspirationally makes sense, though after a time, then you want to check back and reevaluate and see whether the name actually ends up being a good description of the thing that you're doing. It's always possible to walk back ambition, name the thing in a way that fits with what's really happening. So thinking about this, I wondered about whether the name cognitive science should be dropped entirely. I mean, if you haven't yet gotten to the point of science, we could call it cognitive studies or something like that. I then realized that, well, I actually do believe that there can and will be a science of cognition, not just in the faraway future. I happen to specifically believe this because Leverage spent a while studying cognition, and the things we came up with, if they become part of the scientific process, will end up counting as cognitive science, at least many of them. But obviously the research that Leverage was doing was different than cognitive science as it's currently described. This led me to make a distinction between computational cognitive science on one hand and introspective cognitive science on the other. As I looked more into it, it basically turned out, and this is the sort of story of the modern field of psychology, you have this very interesting and important object of study, the mind, and then you have people who very much want to turn the study of the mind into a science. There's psychoanalysis, structuralism, behaviorism. People tried different things. Whatever was discovered or not, these didn't end up being successful attempts to turn the study into a science. As far as I can tell, what happened is after behaviorism, scientists took another crack at turning the study of the mind into a science. And this was inspired by the recent development of the computer. And so that's where the field of cognitive science comes from. Read about the cognitive revolution. So cognitive science in actual practice, or you could say computational cognitive science, essentially is a field centered on the analogy between the mind and a computer. There is an analogy between the mind and a computer. People use this in everyday life. That's enough to make a prima facie case that there's some analogy. And then cognitive science, or computational cognitive science, combines a whole bunch of fields, including mathematical logic, computer science, philosophy, linguistics, and artificial intelligence, basically because all of these have something to say about the possibility of understanding the mind as a computer. Digging into this rabbit hole, I learned a whole bunch of interesting things. Spent a while looking at the mathematical logic and mathematical foundations of computer science. Many of them, as it turns out, are relevant to assessing the plausibility of near-term artificial superintelligence. That's a thing that's been a long-time interest of the leverage community. It's also become a matter of public concern more recently. And so I'm going to talk through a number of different ideas. These are essentially formulated in terms of arguments, and then they bear on a whole bunch of questions, but essentially they pertain to the question of whether the human mind is a computer. In part, I was set on this path I was talking to a few people from the Leverage Network, and these are people who are not particularly friendly to computers in terms of the general ethos. But when I asked the question, is the human mind a computer? The response was, well, what else could it be? I mean, obviously it's not like a box of silicon chips, but it's going to be a computer in some way on some level. I'm going to present a few ideas on this to comment on the relation to the superintelligence question. I want to note that if the human mind is a computer, that doesn't necessarily mean that it's possible to build an AI superintelligence, but it does provide some impetus in that direction. Contrarily, if the human mind is not a computer, that also doesn't mean it's not possible to build an AI superintelligence. You could imagine the human mind is made of pixie dust, but we can get a good mathematical approximation of pixie dust and then code it up. These things aren't definitive one way or the other. To say how one could think about it, the arguments are meant to give, I said, a little bit of impetus. They also give a degree of plausibility for Bayesians. You want to think about how you would update your beliefs if you discovered either that first, the mind was a computer, or alternatively, second, the mind was not a computer. Certainly, the possibility that is more favorable to near-term superintelligence is that the mind is a computer. So if we discover that one, it updates the probabilities slightly, and at least slightly in favor. If we find out the mind is not a computer, we update the probabilities against. It's pretty difficult to tell at this point whether the mind is or is not a computer. There's a basic argument in favor, which is based on an important fact about Turing machines. So now I'm going to go, and with each of these arguments, I'm going to go a little ways into mathematical computer science or mathematical logic. My goal is going to be to keep the things understandable. Questions are absolutely welcome so I can clarify. So let's start with Turing machines. When people think about computers and you want to actually get a definition of computer, the predominant mathematical definition that's used is that a computer is a Turing machine or anything that is equivalent to a Turing machine. A Turing machine is invented by Alan Turing, originator of the Turing test and related things. A Turing machine is a simple machine with a long piece of tape and a head that moves back and forth on the tape, reading and writing ones and zeros in accordance with a finite set of rules. So, for instance, if you have a machine that reads from the tape, and if it reads a 0, it erases it and prints a 1, otherwise it just moves one click to the right, that's a Turing machine. This one would just end up printing an infinite sequence of 1s heading off to the right, and it would never halt. Or if you have a machine that reads the current spot on the tape, and if it's a 0, moves to the left and prints a 0 and then ends, or if it's a 1, then it moves to the right and prints a 0 and then ends, that would also be a Turing machine. The reason that Turing machines are used as the mathematical model of computers is that they were proven by Turing to be incapable of all finite instances of computation. This is a very interesting idea. People now may find it obvious. Imagine a bit more back in the day, it might just seem totally open that you couldn't have a single machine that could do all the different types of computation. Like maybe you could have a machine that could do addition, but for multiplication, you needed something else. And then if you want to do exponentiation, you needed some further thing. The idea that there is a simple machine that can do all the finite instances of computation is an interesting fact. This is essentially why sort of Turing machines are important. Yes, probably multiple reasons for that. But to summarize, something is a computer in the mathematical definition if and only if it can implement a Turing machine, and something is a program if and only if it can be implemented in a Turing machine. So this actually gives the motivation for and some of the substance of an argument in favor of the mind being a computer. The argument is this: the mind, we may posit, is only a finite machine. It receives inputs, some finite set of inputs. It produces outputs, some finite set of outputs, and it does something in the middle. The thing it does in the middle is also finite. All such things can be modeled as programs in a Turing machine, and the mind itself is also able to replicate the effect of a Turing machine. We can follow along and work out what a Turing machine will do. So this means that the mind is implementing some program and is sufficiently flexible to imitate this particular universal machine. And so that means the mind itself is a computer. Now, you might say, okay, the mind does all of that, but it also does some things other than computation. And that may or may not be true. And I guess it depends how you want to phrase it, but the computationalist, and that's what I'm going to call the group of people who largely believe these things, will say, okay, even if the mind does something other than computation, so long as those things are finite, they can be modeled in terms of inputs and outputs from a Turing machine. So essentially all of it can be boiled down into and replicated in a Turing machine, which means a computer. This is the first argument. I said I'm going to consider 4 of them. This is one of the things that motivates the belief that human level or superhuman artificial intelligence is possible. Hofstadter, in, I mentioned Gödel, Escher, Bach, is essentially the computationalist Bible, puts it like this. This is a quote: "All brain processes are derived from a computable substrate. This statement is about the strongest theoretical underpinning one could give in support of the eventual possibility of realizing artificial intelligence." So one may think that the argument works or not. In fact, though, this is something that has been taken as strong motivation in the direction of thinking about the mind as a computer, and then the possibility of human level AI. This, I mentioned, is the first argument of 4. I ended up looking a lot more into theoretical computer science, and as I did, I ended up finding a number of reasons on the other side. It was especially interesting because as I worked through the major named breakthroughs, it looked like most, I would have to check to see if it's all, but at least most of the major named breakthroughs seem, at least on the face of it, to push in the direction of the mind not being a computer. I'm not here going to argue that the mind is or is not a computer, so I'm not going to phrase any of these arguments as definitive or supposedly definitive. What I want to do is just raise them as avenues of investigation. And this is roughly the strength that I meant this first argument to be at. It's proposed that the mind is finite, therefore, etc., the mind is a computer. Sounds plausible at first glance, but you'd really have to dig into the finitude assumption if the argument's actually going to be made good. So same thing with the other argument, and then I'll end up commenting on why I'm not trying to give these as definitive. When people try to argue that the mind is not a computer, the typical thing they do is focus on consciousness and qualia. Consciousness we're all familiar with. Qualia is a term used by philosophers to refer to the subjective elements of experience, the like what it's like part of having an experience. Notably, philosophers typically talk about consciousness because they're arguing about physicalism, that is, whether the mind is physical. In this case, we're talking about a more narrow claim, computationalism, whether the mind is a computer. So we're going to consider a different set of arguments. The first has to do with abstractions and infinities. Let's suppose that I tell you I'm thinking of a number. It's a positive whole number, but it's not 1, it's not 2, it's not 3, and so on. You may immediately infer a contradiction. Why? Couldn't I be thinking of the number 72? Well, you would say that should be covered in the and so on part. And I said it's not 1, it's not 2, it's not 3, and so on. And then the and so on covers 72 or 4 billion or whatever. Okay, so when I say this thing about thinking of a number, but what it's not, that we then end up with a contradiction. How exactly did we see that there was a contradiction? If our minds are computers, then our truth-seeking process is a process being run by a computer, which is to say that it's an algorithm. Any algorithm that discovers things, however, can be represented mathematically as a proof algorithm that works inside a formal system. Formal systems, in turn, are finite sets of axioms with a finite set of inference rules that let you deduce things. So, for example, you can take something like basic arithmetic as a proof system, and you can take a finite set of starting axioms, things like 0 equals 0, and a finite set of inference rules, like from A, and if A, then B, we may infer B. And then all arithmetic proofs can be set up as finite derivations from the axioms in accordance with those inference rules. So that's the idea of a formal system. Going back to the, I'm thinking of a positive whole number, but not 1 or 2, etc. The most literal way to translate this into a proof in a formal system is as an infinite sequence of claims. Let n be the number in question, n is a positive whole number, n does not equal 1, n does not equal 2, n does not equal 3, n does not equal 4. One then infers from that infinity of claims to a contradiction. Now, and this is the part that's important here, formal systems do not permit an infinite number of axioms and don't permit inferences, and as a result, don't permit inferences from an infinite number of claims. I say it doesn't allow either of those. We could derive a contradiction if we let ourselves go from n is not 1, where n is the number I'm thinking of, it's not 1, it's not 2, it's not 3, etc., to the more general claim for any positive whole number x, n does not equal x. Then it would be very, very easy to derive a contradiction. You would set, let n be the number in question, n is a positive whole number, but for any positive whole number x, n does not equal x, contradiction. The key then has to do with the move from the infinite sequence of claims, n equals 1, n does not equal 1, n does not equal 2, n does not equal 3, and so on, to the claim for any positive whole number x, n does not equal x. That move, as far as we normally think about it in the human mind, involves abstraction. That's how we get to the idea that, okay, we're talking about all of the different positive whole numbers. This brings into view one of the issues around whether the mind is a computer. Computers are, as per supposition, finite machines. But note that it seems like, at least at first glance, it's really easy for us to work with infinities. Of course, we don't actually write out all infinite number of the relevant claims. We work with infinities, in this case, through abstraction. The question then is whether abstraction is something that computers can do, or to put it more generally, whether abstraction is itself a finite process encodable into a Turing machine. Computationalists believe that when the mind appears to work with infinities through abstraction, there's a hidden finite process under the hood, so to speak, which is the actual process at work. This may or may not be true, but the supposition that everything the mind does is finite is a claim that's used in the sort of main argument for the mind being a computer. And we should ask, well, what sort of claim is this? I mean, is it, when we say the mind is finite, is this like a pious theological claim? We're not being too boastful? Is it a conclusion derived from observation? Is it like a philosophical idea that everything is finite? There are various reasons which could go into for why computationalists shouldn't be shy or willing to think that it's possible to work with infinities. There is an entire branch of infinitistic mathematics that got developed fairly soon before all this sort of mathematical logic developed that ends up being related that computationalists are very happy with. An alternative might be that you think that the thing underneath abstraction is actually running a finite process because philosophically one believes that everything must be finite, or because maybe you think that physics proves somehow that everything must be finite. There are interesting arguments about the possibility of infinities from philosophy for people interested. I recommend The Critique of Pure Reason, third antinomy. But note how much of a sort of weaker argument it is to say infinities are impossible in principle because of various philosophical reasons. Therefore, the mind is a computer. It's weaker to have the sort of because of philosophical reasons, because we're in a context which we're essentially supposed to be bringing to bear things like math and science, and it's not supposed to be based on one or another sort of philosophical claim. On the issue of physics, you might think, well, physics supports the idea that things are finite. Turns out that this is not yet true. To date, physics is still finitistic, and so the argument could be science will eventually show that everything is finite, and therefore the mind is a computer. But this ends up being a lot weaker for the same sort of reason. When people are presenting the idea that the mind is a computer, it's usually not stated that included is the supposition that physics will develop in a particular way and we will eventually figure out that everything is finite, and so essentially computers are the upper limit for capacity, or that there's some philosophical position that's being used to rule out infinities. What we're usually trying to do in thinking about this is trying to assess what evidence is available now, and without having to use one or another sort of surprising philosophical argument. Okay, so I just talked about abstraction. Abstraction is one of the potential stumbling blocks for the proposal that the mind is a computer. There's another one that has to do with the idea of truth. So Alfred Tarski, one of the mathematicians who's investigating the idea of provability in formal systems, managed to prove, and this is one of the sort of highlighted results from early mathematical logic. Tarski managed to show that the concept of truth is not definable within a formal system. Let me try to explain what this means, because this is a very surprising thing. Formal systems, like if you have your axioms and then you derive things from the axioms by means of a finite set of inference rules, they're essentially meant to help encapsulate provability so that provability can be understood. You know that provability is being identical to one of the axioms or following from one or more of the axioms in accordance with the inference rules. But because all of that is defined, the concept of proof then becomes definable. And while proof is definable inside of formal systems of sufficient power, Tarski managed to prove, and this is a result, and I will sketch how he got there. He managed to prove that while you can define truth in formal system S by using another formal system T, so that truth in S is defined in T, you can't define truth in S or truth in T in T. The actual proof here uses the concept of Gödel numbering, where essentially mathematician Kurt Gödel figured out how to encode propositions about formal systems into numerical statements, and then use those encodings to talk about the formal systems themselves. Tarski figured out that if you can define truth in a given formal system, you can define the formula X is not true, but then use the Gödel method to get it to refer to itself, yielding a proposition that essentially asserts of itself that it's not true. If you have a proposition that asserts of itself that it's not true, you get a contradiction, since the statement, if so, say you take the statement, this statement is not true. Is it true? Well, if it's true, then it's not true, because that's what it says. But if it's not true, then the statement, this statement is not true, is true, because it says that it's not true. And so either way, you get a contradiction. People familiar with philosophy, this is the liar's paradox. The interesting thing is that Tarski showed how if you use Gödel encodings and your formal system has the concept of truth, then your formal system can get to be made to assert the liar's sentence, or it just does assert the liar's sentence in a manner of speaking, which gives you a contradiction. If your formal system has the concept of truth in itself, then you get the contradiction from the liar's sentence. Conclusion, there's no way, if your system is consistent, to define the concept of truth. And that's one of the famous results from mathematical logic. And then applying this now in the context of the mind, we introspect briefly, and we find that our minds have a concept of truth. Moreover, the concept of truth that we have is the concept of truth in general for itself. It's not meant to apply to some specific formal system. It's meant to apply for itself. And so that we call the mind M, the concept of truth is certainly meant to apply and hold in M. This means from Tarski's undefinability theorem that either the mind is not a formal system, or if the mind is a formal system, then the concept of truth we're conscious of in the mind isn't the actual concept of truth for the mind. Now, again, I'm not here trying to present knockdown philosophical arguments. The context is one of science and mathematics where philosophy has gotten mixed in and people have become confused. So I'm not proposing that because truth is undefinable in a formal system, but truth is, I'm not saying because truth is undefinable in a formal system, but is definable in the mind, the mind is not a formal system and hence not a computer. For that, more consideration is necessary. We'd want to examine the concept of truth. If people are interested in that, I would suggest starting with Aristotle's Metaphysics, where he proposes that truth is, quote, to say of what is that it is, and of what is not that it is not. Again, the purpose here is to suggest avenues of investigation, but it's notable that if the mind is a computer, running an algorithm that can be construed as a proof algorithm in a formal system, then the concept of truth available to introspection is not the concept of truth for the mind as a formal system. One may then wonder if one is thinking through computationalist philosophy carefully, what the concept of truth would be whenever anything is asserted, because on pain of inconsistency, one would not want to assert that one's own assertions came from a formal system and used a concept of truth that was definable within that system. Okay, that's Tarski. And we looked at omega consistency, as it might be called. That's I'm thinking of a number one, which was introduced by Gödel when he did his incompleteness theorem. I have mentioned Gödel a few times. Notably, I have not yet gone into Gödel's incompleteness theorems. Gödel's incompleteness theorems, in particular, the first one, are relevant, which is why they often come up in these contexts. So when people talk about whether the mind is a computer, you either, and if they say no, you either expect that it's consciousness and qualia, and it's a debate about whether the mind is physical, or they're going to talk about Gödel's incompleteness theorem and talk about how this means that the mind can't be a formal system. This is, in fact, the most common argument that is used. There are three camps, and so I'm going to sketch Gödel's first incompleteness theorem and then talk about essentially the whole situation. So, as I mentioned, Gödel worked out a clever way to encode propositions about formal systems into numerical statements and then get those statements to refer to the formal systems themselves. This makes it so that you can construct normal mathematical statements that have implications about things like truth and provability inside the formal system. Rather than looking at X is not true, which is the one Tarski looked at, Gödel looked at the proposition X is not provable. Notably, X is not provable in system N. Remember, the idea of a formal system where you have the nice axioms, the nice rules of inference, and you can see how everything is derived, is meant to make it so that provability is something that is very well understood and can be reasoned about. Gödel uses the encoding method to construct a arithmetical statement that corresponds to the assertion that this very statement is not provable. In particular, not provable in system N. So with the Tarski one, you get the liar's loop. The thing that Gödel did is that he constructs this statement that is the equivalent of saying that this very statement is not provable in the system. And then we can ask, is it provable in the system? Well, if it's provable in the system, then it's true in the system. But it says that it's not provable. So if it's provable, then it follows that it must not be provable, since it says that it's not provable. But if it's both provable and not provable, then the system is inconsistent. So if the system is consistent, it follows that the statement isn't provable. But you'll note that the statement is just that it's not provable. It follows that the statement is true. It follows that we have a statement for the formal system that is true in the formal system, but not provable in the formal system. That's the high-level run-through of Gödel's first incompleteness theorem. And then essentially, Gödel provides this method where for any formal system of a certain strength, you can generate a statement that's true in the system, but not provable in the system. Let's call the statement that gets generated for each system the Gödel sentence for that system. This is as the terminology is used. The disagreement about the incompleteness theorem and the mind doesn't have to do with the part that I just described. Everybody, all three camps, agree that Gödel's proof works. And so they agree that for any given formal system, there is a method that can be used to generate a particular sentence, which is true in that system, but cannot be proven in that system. The disagreement pertains to what happens if we take the Gödel sentence of the human mind and feed it to itself. So let's unpack this. Assume that the mind is a computer running an algorithm. Construe the algorithm as a proof algorithm. I mean, one thing I should say when I say that, the reason why, as far as I can tell, this was called cognitive science is that we're studying cognition. What is cognition other than thought? Cognition is mental activity or intellectual activity insofar as it's aimed at truth or knowledge. And so you could think that the mind does all sorts of things like regulates your heart rate and so forth. But what you can do is look in particular for whatever the mind is doing and find the truth activity. If the mind is a computer, then all the things being done by the mind are going to be describable as algorithms, and then the truth activity itself will be describable as an algorithm. You can then take that and construe it as a proof algorithm inside a formal system. So there will be a formal system that the proof algorithm is running in, where the things that the mind outputs as truth are derivations from the axioms of the formal system. So that's what's entailed by the idea that the human mind is a computer in this context, is that there is a formal system that in principle could be described, that has a proof algorithm, and that proof algorithm is the thing that outputs the result of the human mind as it attempts to generate truth. By Gödel's argument, if the mind is a computer, and hence there is this formal system, etc., then there is some sentence, we can call the human Gödel sentence, that's true for the human mind's formal system, that's not provable by the human mind. And moreover, this statement is a statement of essentially arithmetic, and Gödel has given us a formula for generating this statement. One way of thinking about the first incompleteness theorem is that the conclusion is that formal systems all have blind spots. There's a surprise place which can be specified that the formal system just ends up being able to not prove something, even though that thing is actually true from the perspective of the formal system. So if you think of formal systems as all having blind spots, and you think, then well, it's a really interesting question. What happens when you interact with the thing's blind spot? If our truth-seeking function is construable in this way, then this means that the human formal system has some blind spot. And then there will be something in that blind spot which is true, but which we won't be able to prove. And we have a formula for generating it. This is the thing that generates the confusion about what might happen. Some people, like John Lucas and Roger Penrose, have argued that, of course, we would be able to generate the statement and prove it. It's like, well, suppose somebody comes out and they're like, look, this is actually the formal system of the mind. Then Lucas and Penrose and people in this camp are thinking, great, take the formal system, use the Gödel method. The Gödel method is this mechanical method. You can make a computer that would do it. You go through and you produce the Gödel sentence. The Gödel sentence will be true. And we'll know it's true because the thing that gets produced is something that's true but unprovable by the system. But since we know it's true, we've just proven it. And so there's some sort of contradiction, and they say, yeah, the contradiction is that you didn't actually get an axiomatization of the truth-seeking function for the mind. You didn't end up with the right formal system. And we would generalize, or they would generalize, it doesn't matter what the formalization is. Any formalization, we can take it, we can run it through Gödel's method, it'll pop out the Gödel sentence, and we will know by that exact method that it's true, which means that, I mean, if it really is our mind's, the formal system for the mind, we wouldn't be able to tell that it's true, but we could conclusion, no such formal system with any proof algorithm is going to correspond to the truth function of the mind. This is camp one. Camp two, which I think includes Hofstadter, but I haven't been able to find the reference. If anybody happens to find it, please let me know. Other people suggest that if you manage to figure out, you get the axiomatization for the relevant human formal system, and you try to go and prove or try to get the Gödel sentence, which if you know that you've done it, then you will have proven it, then the mind will just glitch. The question here is you find your mind, if all formal systems have blind spots and the mind in the relevant sense is a formal system, the mind has a blind spot. What happens if you go look at the blind spot, answer, you don't see anything? How does that actually look in reality? Well, maybe you just keep zoning out. You're like, well, I know that if I do this formula, I'm going to produce something in my own blind spot. And I keep zoning out every time I get to step 78. That could be one way it goes. That's what camp number 2 says. And then camp number 3, and this, according to Wikipedia, says that this is the, quote, modern consensus in the scientific and mathematical community, conclude that human reasoning is inconsistent. Gödel's proof only works if a formal system is consistent. If it's inconsistent, it can prove anything, including a statement that encodes the proposition that that statement can't be proven by that system. This is the one place I do want to push back. It's not the consensus in the modern scientific and mathematical community. Actually, of all the different answers here, I think this one is the least plausible. It's certainly true that people are sometimes inconsistent and sometimes make mistakes. But the real question is whether the human proof algorithm, and this can be thought of for individual humans or humanity as a whole, since the same argument applies. If you have the whole, if you have all of humanity, and then you just think of humanity as implementing a big meta computer, which would still be a computer, the question is whether that algorithm halts on an inconsistency. It's very, very easy to imagine the mind as a computer, a simple Turing machine, printing ones and zeros on a long tape. The output of the mind comes when the machine actually halts. You could code a Turing machine that makes mistakes in computation and then corrects them as part of getting to the actual answer to some mathematical question. We could have an addition problem where it's supposed to add 2 and 3 and it prints out some ones and some zeros and some more ones, and the ones correspond to what it's supposed to add, but it prints 1 too many, though there's some way that it would be able to detect this, and then it detects this and goes back and fixes it and then ends up giving the correct answer. You can have it be that some algorithm in the process of operation makes mistakes. The question is what the thing actually ends on. And then you might say, well, the human discovery of truth is limitless and will go on forever. And with science, and we never actually end on anything, and we can always revise previous answers. That's fine. But if you really take that seriously, then you can't construe the human mind as a computer, because the output of the human mind is what happens when the thing halts. And if the thing never halts, then we'd have to say it had no output. That's like a funny thing to say, but not the right way to think about it when you're trying to analogize the mind to a computer. Instead, the thing you'd want to do is you want to come up with some halting condition. Maybe it's after something's been accepted for long enough, or maybe it's accepted by enough people, or it's been accepted and put to various types of tests, or something else. But whatever the halting condition could be, should be, that's the thing to look at. And so on this third option, humanity should be able to generate and prove its own Gödel sentence. And we should be able to stare at it and stare at the contradiction, like stare at the proof that we cannot prove this thing that we've just proved. You absolutely can imagine this happening. Like, you can imagine a circumstance where humanity figures out its own algorithm, uses this to generate its own Gödel sentence, uses this to show that we cannot prove that particular sentence, which if we've shown that it's the Gödel sentence, we know, because that's what that one is, but also that it's true. The thing that would need to happen is something much closer to figuring out the algorithm for the human mind, generating the unprovable thing, proving that it's unprovable, proving that it's true, holding up that it's unprovable, and that we've proven it right next to each other, bringing all the mathematicians and logicians in the world together and having them hold up the law of non-contradiction as we all stare at it, and then we still think that it's right. You could just imagine this happening. It's a really surprising circumstance, but you could imagine that we're like, usually I don't like P and not P, but in this case, it seems fine. Yeah. And everyone's like, yeah, no, I think this is good. And then we enshrine it in the big list of things that humanity has proven right there after 2 + 2 is 4. Like, you can absolutely imagine that happening. But that's the sort of thing that should be imagined if we're imagining that the resolution to this is that the correct axiomatization of the human mind is inconsistent. So I don't want to say that that's not going to happen. It is my personal belief that that one is much less likely than the other ones, but I do think that it's not actually the consensus of the scientific and mathematical community, and so someone should update the Wikipedia page, because, I mean, reading through these things, occasionally you find things that it really looks like the person who edited it was upset about one or another argument and wants to overstate. So anyway, there is some glitch there. Okay, getting close to the end. So you might ask, so I've just given all the different arguments, right? We've got the mind is a computer because finite. We've got the mind is not because abstraction and infinity. We've got the mind is not because it is a concept of truth, and truth is not formalizable inside of a formal system. And then we've got the Gödel argument, which is that feeding, well, and then that one I haven't actually given an answer. So you might say, okay, what happens when the human mind tries to prove its own Gödel sentence? And then you might also want to ask, how does all of this relate to an empirical approach to cognitive science? So that's, after all, the title of the talk is an empirical approach to cognitive science. And thus far, I've just been talking about mathematical computer science and formal systems and philosophy. The answer is that it's important to distinguish the different ways of investigating the mind. One of these is philosophical. It lends itself to long arguments using important concepts. You get treatises, you get books on topics which individual people read. There's a different way of investigating the mind, which is scientific, which relies on observations and tests, where a community engages in a process of mutual checking and correction using those observations and tests. So we have philosophical and scientific. You can distinguish them by their form. They look different. There is another way, a related way to investigate the mind, which is empirical. The concept empirical means that knowledge, the relevant knowledge, is derived from experience. The opposite of empirical is a priori, which is Latin, which means the knowledge is somehow achieved prior to or independent of experience. Empirical is not the same thing as scientific. Scientific research is empirical because science depends on observations, which are made through experience. But scientific also means that it feeds into this group process of checking and correction, and there are plenty of empirical things that are not scientific in that sense. For example, my investigation of cognitive science as a field was empirical. If I was just doing it a priori, I might look at the words cognitive and science and conclude that cognitive science is the science of cognition. In fact, cognitive science to date has been the investigation of cognition largely on the basis of a proposed analogy between mind and computers, and that's a result I reached through my experience of the field rather than deriving the answer from ideas alone. Now, we can, of course, ask how the computer-based investigation of the mind has gone. The answer appears to be rather poorly, at least if one takes Wikipedia and the standard histories of artificial intelligence seriously. As I mentioned, Wikipedia is weak on actual discoveries made by the field. It's possible there are some important discoveries that haven't made their way onto Wikipedia. In that case, hopefully someone will find and report them. But the other reason I mentioned has to do with the history of AI. If you look at the history of breakthroughs in AI, you see a celebration of many milestones. You have defeating human world champions at different games like backgammon, checkers, chess, Jeopardy, and Go. We also have the recent passing of the Turing test by large language models, generation of high quality images with diffusion models. Notably, as far as I can tell, none of those breakthroughs are particularly mind-inspired. Some are algorithmic, like beating checkers by brute force. Some are brain-inspired, like the deep learning model that beat humans at Go, or the transformer models underlying LLMs. I'm still learning about the history of AI, but as far as I can tell, cognitive science methods have largely, if not completely, failed, and the advances in AI are the results of other methods working instead. That's not to say that the mind-inspired approach to computers couldn't work, but from an empirical perspective, I have begun to wonder if the computational version of computer science is a research program that, a computational version of cognitive science is a research program that has been much more generative than it has been fruitful. You can have a thing that generates many ideas. It's fruitful if a bunch of those ideas end up being able to be confirmed to be true. Maybe what we have is something that generates many ideas and they turn out to not end up being true. It could be that there's subtle influence such that the computational cognitive science is some way feeding ideas into the other more connectionist and brain-inspired approaches. I don't know if that's true. That's an interesting subject to examine. And it's also certainly possible that the study of computer systems will help us to understand the mind in the future. There are now actually artificial minds worthy of the name, the chatbots produced by OpenAI, Anthropic, Google, Meta, and so on. These are recognizably mind-like. Are they conscious? Bracket that. We might be able to learn something about human minds by studying these artificial minds. There's a small field now of interpretability research that's trying to figure out what's actually happening inside large language models, because we don't actually know. That is the thing that I mean to contrast that to, rather than arguing in general in the abstract that the mind must be a certain way and basing research programs on that, taking existing artificial intelligence models, the ones that are good enough to be thought of as minds, and studying those, at least that's an empirical approach. At least you're looking at reality and trying to figure out what's happening. Now, of course, the route that I think is the most promising by far is investigating the mind introspectively. We could thus distinguish, as I have suggested, computational cognitive science from introspective cognitive science. Here's the place that I actually think we may end up with a science worthy of the name. Why introspection? Well, first, introspection is the reason that most people think there's a mind in the first place. If the object is first detected by means of instrument X, it would not be that surprising if one could make progress understanding that object also by means of X, whereas other methods might help as well. But the idea here is thinking like telescopes will help us understand asteroids better. Why do we think there's asteroids? Mostly telescopes, and then maybe the telescopes will help us understand them better. Second, introspection is already being used to study the mind. When we think about things like when I propose the contradiction for I'm thinking of a positive whole number, it's not 1, it's not 2, it's not 3. When we notice that we have the concept of truth, what we're doing is we're using introspection to identify something about the mind that may or may not indicate inconsistency with being a formal system. Third, introspection is relatively inexpensive. We all have minds. Training introspection for lots of people is not that difficult. There are lots of interesting questions to answer, including how the human mind is able to implement arbitrary algorithms. The mind may or may not be a computer, but is at least able to implement a computer sometimes. There's a question of how it does that. Fourth, it seems very unlikely that we will get to a good account of human verbal behavior without referencing the mind in some way. The behaviorists tried to explain human behavior without reference to the mind, but they got stuck, among other places, on explaining verbal behavior. Note that the recent set of advances in AI come from essentially large-scale imitation of human verbal behavior. Getting an account of that, very hard, seems very hard to do without the mind. And last, there's already been a bunch of progress made, though not everyone admits it. We learned a lot about the mind from Freud, including about the existence of analyzable mental structures. It has been the experience of many therapists and many regular people that mental structures can be explored introspectively, which makes sense if they're actually there, which there is good reason to believe. Above all, whether one favors introspection or not, we need an empirical approach to cognitive science. Philosophical arguments are great. Anyone who knows me knows that I love philosophical arguments. But unless the philosophy is executed really, really well, it's easy for deviations to creep in. Eventually, you find yourself in a world where it's hard to even think of alternatives, even though there are plenty. I mentioned that part of this investigation was motivated by talking to people who ask, well, what could the mind be if not a computer? Here are two suggestions. And we should say alternative to being merely a computer, because the mind can, at least in a limited way, implement a computer, because we can sit there and we can implement a Turing machine. First, the mind might implement an uncomputable function. There are plenty of mathematical functions which are perfectly definable and yet are not computable. Solomonoff induction, which is a formalization of Occam's razor, is one of them. The busy beaver function, a fun name, that ends up being an important function. That's another one that's definable but not computable. Leverage's introspection research turned up a lot of evidence that the mind updates in a way that explains sensations and maximizes local elegance while maintaining the belief that the basic goals will be achieved. As stated, whether this corresponds to a computable algorithm is determined by the space of possible belief systems. One can imagine computable versions, though whether these would need to simplify what the mind is doing or whether they would be computationally tractable is unclear. Second, the mind might not implement a function at all. Functions, as they are classically understood, are finitely definable and need to avoid certain types of self-reference. Some types of self-reference, such as recursion, are fine, others are not. There does seem to be something strange going on with infinities, self-reference, and the mind. The way forward here will almost certainly be more philosophy, which proceeds in advance of science, but takes into account advances from mathematical logic and also the best existing models of the mind, be they computational or conceptual. It will be useful to demarcate that philosophy, mark it clearly as such, and present it as clearly as possible so people don't lose the ability to conceive the alternative. Those are my prepared remarks. Happy for questions.
Hey, Geoff, is this written down anywhere or expected to be?
Yeah, so we're experimenting with and plan to both do like video content, but then also release companion pieces, basically. We haven't gotten to a reliable production schedule yet, but we currently have pieces that are going to go through and talk about each of the important concepts in mathematical logic and computer science. So the Gödel one, for example, the Tarski one, that deserves its own thing. There's going to be one that close to done, which is whether the mind is a computer. There's going to be a different piece, which is on the history. There's basically this talk weaves together two threads, maybe. One of them is, here are some arguments and philosophy. What does that mean? And can we like hold that over in its own philosophy zone while we think about what's happening, in a way that it's more visible. The other is distinguishing some of the arguments, and the other is the sort of the distinguishing of those. And so we have a piece that's going to go through and talk about the history and talk about the difference between natural philosophy, which is what this is natural computational philosophy, and science. And then there are going to be notes just for this presentation itself.
Cool. Perfect. Thanks.
I don't know if I should be shocked by it, but one of the things that I ended up being a bit shocked by was the fact that, looking at the Gödel's incompleteness theorem argument, all the people are trying to resolve it on a theoretical level only, as opposed to clearly stating the conditions and experience that you would see and the crucial experiment that in principle could be run. You might want to try to figure out what the answer is going to be before you run the experiment, but at least describing the conditions clearly. And so you could quip that, well, of course, the philosophers want to resolve it philosophically. They don't want to pass it over to the scientists and the mathematicians and the theoretical physicists who are very, very, very close to mathematics. They don't want to pass it over to, regular old tests and so forth. But it just seems to be a fact that if we got a nice formalization, you could get a really good predictive theory of what the mind is doing. You could imagine formalizing it. You could imagine using Gödel's method to produce the blind spot. You could imagine then what happens as people try to look at it. It's like, it's a great question.
It sounds like this, there's been the reference to people being unable to consider an alternative.
Yeah.
It's like, if the mind is not a computer, then what is it? It feels like a reasonable thing that people are saying. What would it look like if one of these possible alternatives was explicated and we were like some amount of time down the road of that being the case? It's like, do you have some sense of like what that would like feel like to live in a world where like everyone was like, of course the mind isn't a computer, it's this other thing? Do you expect any like knock-on effect of that, or is that going to be like a technical thing that people in the introspective cognitive science field think about, and it doesn't really affect anything else?
I could imagine an alternate history where psychology or introspection came out first, where we then understood that. And so I'm going to use the leverage introspection connection theory version because it's the one that I know the best. So there's an interesting thing there where the main theory of mind I mentioned the updating beliefs elegantly and locally, et cetera, et cetera. There's this term in the description of the updating function, which is elegance. Elegance is very similar conceptually to simplicity. Simplicity is frequently captured in the idea of Occam's razor. Occam's razor there's one way of formalizing it, which is this thing called Solomonoff induction. Essentially, what it does is it has a way of assigning the complexity to different hypotheses and then assigns probability in inverse proportion to the complexity, so that the simpler the hypothesis, the higher the probability, and then it updates from there using the Bayesian, using Bayes' theorem. Notably, so Solomonoff induction is not computable. There is a computable simplification where you can tell because something like there are an infinite number of hypotheses. And because there's an infinite number of possible hypotheses, even if you apply smaller and smaller probabilities to them as they get more and more complex, it's just your computer can't handle the infinity. So then some researchers took Solomonoff induction and made an AI based on a simplified version of it, like a finite implementable version. This AI was called AI-XI. It was able to do things like play Pac-Man, but it also was very cumbersome. And as far as I understand it, the researchers gave up on that line because the simplification of Occam's razor, the finite version of Occam's razor, ended up just being too computationally complex, or sorry, too computationally intensive. Looking at the connection theory version, you have this concept elegance. There's no stated way to detect the elegance of a hypothesis. One might be able to come up with one. The thing that people actually do is they use their own minds to detect the elegance of a hypothesis. So if I describe to you a hypothesis and you're like, no, that's implausible, frequently you're employing a version of Occam's razor. I'm going to say, okay, think about that in terms of elegance. But you could imagine a world where psychology and introspection came out first. It's well understood that, suppose this is the future that ends up happening, it's well understood that elegance is one of the key features. It is then also well understood that any artificial intelligence system that replicated the function of the human mind would need to implement a concept of elegance or some simplification. And then you could imagine just finding that all the computer programs that tried to implement simplifications of elegance were terrible, and they could like play Pac-Man, but then would, you know, roast your computers and require way too much processing power. And so that in practice, people only could ever really assess elegance by using the human mind, and that all of the computational methods that were employed ended up not working. You could even imagine maybe somebody proves that you occasionally get complexity type proofs, so that you find out that as you scale up the computation, it becomes harder and harder to do at a very fast rate. You could get computational intractability results or impossibility proofs that show certain types of limitations. If this happened, then what would happen would be that artificial intelligence would understand that if it was trying to replicate the human mind's effect, it would either need to be going by some very different method or coming up with some feasible knockoff version, and then it wouldn't be expected to be much better, at least along the dimensions of the assessment of elegance. And so then that doesn't fully rule out that you get things like superintelligence, but what it does is that the space of hypotheses is much, much more constrained. So then people are like asking, okay, sure, the AI can't do real elegance, but it can do elegance prime. Elegance prime is about 80% as good. That's pretty good, but also we can make the computer do these things much faster. And so then you get speed superintelligence rather than cognition superintelligence. And that's, I'm just sketching, but I could imagine all sorts of different paths that are possible. And I can also imagine way weirder ones that I'm working on figuring out how to explain. But the one I described is pretty simple. It's just the if introspection came first. There's actually going to be an entirely other branch that has not yet been thoroughly explored as far as I can tell, which is the degree to which, so computers have this totally amazing advantage, which is that they're the universal Turing machine. It can implement any describable algorithm in principle. The computable ones, you can describe some that aren't computable, but it can implement, you know, all the finitely implementable ones. There's an advantage to that, which is that it might be really, really hard to get the human mind to multiply numbers, whereas you can get a Turing machine to multiply numbers way more easily. Note that multiplying numbers is something that seems really basic, doesn't have much to do with what humans seem to have evolved to do. But there's a trade-off. The universality also means that if you want it to do some specific function, and there's my intuition says, look at the no free lunch theorem here, but I haven't gotten there yet. You just have a disadvantage because there are going to be some things. It's like, you know, you could make a computer program to implement a gear or to like functionally implement what a gear does, but maybe a gear does it better because the gear is actually specially tuned for that. If this is the case, then there's going to be this whole other question of whether general functions are more powerful than specific functions. And this is going to break into biology. There's so many, I think this is incredibly interesting. And I want to figure out how to get all the sort of like relevant thoughts into an area, lay out all the arguments nice and clearly, and then draw a nice line and mark this natural philosophy. It's the perspective here, and this will be included in one of the upcoming publications, is that natural philosophy is really fast. When you think, you can get through conclusions. You can, inference to inference to inference. You can get to conclusions. Getting the rest of the scientific community to catch up, that's like a longer, slower process. And then, and this is something that I haven't figured out where to write this up, but there's a major problem with having all the pronouncements of scientists count as authoritative, because then they can't jump ahead 18 inferences and do natural philosophy. I want to create some zone where there's the natural philosophy zone where no one's supposed to officially listen to anything that anybody says, and we're allowed to figure out what's going on in reality. And then you have the more authoritative area where things have been established to the satisfaction of the scientific community, and we try to make that go as fast as we can. One thing that would be helpful feedback and could be later. I didn't go through in this talk and specifically talk about the way that Kurt Gödel figured out how to get statements to be encoded to refer to facts about formal systems. It is a current commitment of Leverage as an institution that all these things can be explained in fact clearly and in fact simply enough. And so we're very interested in getting the explanations to be clear enough that people can actually think about them. So noting that I didn't do the full thing for Tarski or Gödel. Any places where the things could be explained more clearly would be very helpful. Getting it to be that people can actually think about these questions is going to be really important for getting there to be like healthy public support of investigation in general, whether that's natural philosophy or science. The TLDR is, I love arguments, maybe you love arguments, that's great. And you can tell whenever, anytime things get really argumentable. You can just see all the arguments clustering together, and then people are saying, draw a nice little box around that, put that over here. That's good stuff, but shouldn't be allowed to bleed in and affect everything else. Okay, there just will be ways to conceive the alternative of a bunch of hypotheses. And then one of the things that's great about science is that the fact that everything ends up getting pegged to observations means that we don't have to end up agreeing on the interesting curly cues of arguments. We can try, but observations just empirically are more effective at getting people to actually advance together as a group. One last thing, which is that I think that maybe the alternative, in some sense, the thing causing the problem is ideology, where if you can't get everybody to agree to complicated arguments, you can try to produce ideology that gets everybody motivated in the same direction. That has the useful advantage of making it really easy to get lots of adherents and then eventually funders, and then you can fund really large projects and so forth. But if your ideology ends up being mistaken, then you might end up accidentally spending ungodly amounts of money on things that will not have made sense in retrospect, because it turns out that a bunch of the basic suppositions that led you down that road didn't end up being true. Obviously here I'm referring in part to AI. I will say that Sam Altman's choice to dump a bunch of money into large language models is the thing that caused the breakthrough that made it so that we actually do have legitimate artificial minds now. So like, that's great. That's an actual scientific achievement. In some cases, yes, dump money on it. I'm actually not just thinking of AI. There are all sorts of places where the scientific reasoning is, well, it has to be X, and we haven't detected it yet. So let's try again, because there is a series of arguments that have painted people into a corner, and that ends up with lots and lots of effort being wasted, and then ends up being bad for science and people in the long run, because the thing we really want is stuff that works. My contribution to ideology will be a little bit of anti-ideology. Any last questions or thoughts? All right. Thanks everybody for showing up. Hope it was interesting. All right.